that I've got this equation with that relates the rates, what am I going to do with it? So you have to think about what this question is really asking us to find, for one thing. So the question asks, at what rate is the area of the fire expanding? So what that's really asking to us for is the rate of change of the area in time. So that is dA dt. That's what it's really asking us for. All right, so that, in fact, is this. This is dA dt. That's what we're looking for. We're looking to find out what dA dt is. All right, and what about this fact that the radius is expanding at 2 meters per minute? Okay, what that's really giving you is the rate of change of distance, well, the length of the radius, you could say, with respect to time. So that's dr dt. That's what they're giving us. So they gave us dr dt, and we're trying to find dA dt. So when we're looking at this 2 meters per minute, what we're really looking at is that dr dt equals 2 in both cases. So now we've got things that we can sub into this equation. So we know what we're solving for. We're solving for dA dt. And we know what we can plug in. We know that dr dt equals 2, so we can plug that in for the dr dt. All right, but now I have this problem. I need to know what the r is. Well, I can figure out the r because I know it's expanding at 2 meters per minute. But what I want to pay attention to is I have an equation that relates these two rates. I know the rate that was given. I know which rate I'm trying to find, but I might need to find some additional information to figure out something for the context of the problem of a variable that I need to solve for. So in fact, I need to solve for r. I need to get information exteriorly about what r is, exterior to this equation. So I need to know what r is in each case. So if we think about part A, when t equals 10 minutes, all right, then at t equals 10 minutes, well, what we can know about the radius is that since the radius is expanding at 2 meters per minute, what that really tells us is that r is equal to 2t. That's just the old distance equals rate times time, right? Where here, the distance is the radius, the rate is 2, and the time is the time that's given in the problem, all right? So that tells us that the radius at 10 minutes is equal to 2 meters per minute times 10 minutes, which is equal to 20 meters, all right? Probably a little more analysis than I had to do in order to know that after 10 minutes of moving at 2 meters per minute, you've gone 20 minutes. I mean, you could also consider that to be obvious, all right? But here it is written out as an equation anyway. So for part A, when t equals 10 minutes, then dA dt equals pi times 2 times 10 times 2, right? So the dr dt is from here, that was 10, and the r equals 20, that's from here. So we basically just plugging those values in. All right, so that equals 40 pi. All right, and that's a number that would not be very useful to the fire management people who are concerned about the expansion of the fire. So maybe we'll help them out by doing 40 times pi on our calculator. And we could of course estimate it's going to be 120, but it's actually 125.664. 125.664. What do you think the units are for this? If dr dt is really 2 meters per minute, what do you think the units are for dA dt? Well, area is measured in square meters, so that's square meters, and time is measured in minutes, so it's square meters per minute. All right, you can do an analysis like that. Look at the numerator and denominator of the derivative. The A is measured in meters squared, time is measured in minutes. You get your unit analysis, you can do that way. All right, well, what about part B of the problem where t equals 20 minutes? Is the fire going to be expanding at the same rate? Is it going to be adding the same number of square meters per minute? So I already gave you the hint that it's no. But see, notice how we have to find the r. In this case, t equals 20 is going to be different. The r is going to be different. So 2 times, this time it's going to be 20 minutes. So the radius is 40 meters now. So the difference between these two problems is essentially that at 10 minutes, the radius of the fire was only 20 meters. Now the radius of the fire is expanded to 40 meters, right? And then when I come back to my equation here, dA dt equals pi times 2, and now my radius is 40 times my dr dt, which is still 2. All right, and now I get, 160 pi, right? I'm just surprised that it's 4 times as much, but it actually makes perfectly sense why it's 4 times as much. 160 pi meters squared per minute, but let's again, for the sake of the poor fire marshal guys who didn't bring calculators with them, they're plenty clever enough to figure it out, but they didn't bring their calculators because it's a fire, and it's gonna get your calculator all smoky. All right, 0.655, that's what 160 pi is, meters squared per minute. So yeah, actually it does make sense in a way that the area is expanding 4 times as fast, right? The time that has lapsed, it's double the time, but the rate of area expansion is 4 times as much. And that's because the relationship between the radius and the area goes by the square. So if we did 10 minutes and 30 minutes, it would be 3 times as much time. It would be 9 times the rate of area expansion. If you want to think about that, which you don't have to. The key elements here are, we got an equation, let's find a contrasty color. We got an equation that relates the 2 variables. We did dA dt. We plugged in the information that we were given, but we had to seek some of that information out in an auxiliary calculation, and then we were able to solve for the rate that we wanted. That's the process. So in fact, we can summarize that like this. And I recommend that you download this sheet if you have not already. The steps for solving a related rates problem. We are going to collect all the given information, recording the rates of change as ddt. That's just one way that helps me to organize the problem, because a lot of these problems have a large amount of given information. So you kind of have to get organized about how you're going to notate all that. Look for things that are rates and make sure they're d something dt. So for example, we needed to know that rate that the radius was expanding was dr dt. I also like to make a note about what the question is. So the question asks us for dA dt. So I usually make a note of that. dA dt is the question, because it also asked us for a rate. So anything that's a rate is ddt. One thing we're going to watch for is anything that's getting smaller is going to have a negative ddt. Hopefully that makes sense to you by now. Decreasing means the derivative is negative, and it's common sense as well if you think about it. In this case, the fire was expanding, so everything's getting bigger. So all our ddt's were positive. Then we write an equation, step 2, write an equation relating the variables. That's what we did here. So sometimes you got to use your geometry knowledge. Sometimes you look for it in the problem. It's there. There are different ways that this equation could emerge. Then we're almost always going to do this step, I think pretty much always, differentiate implicitly, usually with respect to t, but not always. I think almost all of it is going to be with respect to t, because when we talk about things changing, we're usually talking about things changing in time. But not always. All right, and so that's what we did, differentiate implicitly. And then step 5, sub the known values, and you may have to use given information to solve for desired quantities, right? So we subbed in our known values, we did some auxiliary calculations to find some things we needed to know, and step 5 is solve for the unknown rate. In this problem, the unknown rate just was automatically the result. Sometimes your rate that you want is going to be buried in the equation somewhere. You have to dig it out by solving. All right, so this is the basic process for solving a related rates problem. We will now go to a certain page, page 251, and we'll start doing some of these.